all about atoms. Atoms are like the Lego bricks of the universe. They're tiny, they fit together in specific ways, and they build everything we see around us. But instead of little plastic blocks, atoms are made up of even smaller pieces: protons, neutrons, and electrons. Subatomic particles. So what are these tiny bits? First, we have protons. Think of them as the positively charged VIPs hanging out in the nucleus, which is the atom's core. Then there are the neutrons, chilling in the nucleus, but with no charge, just keeping things neutral. Lastly, we've got the speedy electrons, negatively charged particles zipping around the nucleus like they're in a high-stakes game of Fortnite, dodging every other player. Locations in the atom. Protons and neutrons are the nucleus main residents, while electrons zoom around the outside. Because electrons are so fast, we can't pinpoint their exact location at any given moment. So we represent their general area as an electron cloud, like a blur of motion that's always on the move. Measurements of charge. Protons have a positive charge, and electrons have an equal but opposite negative charge. Imagine two teams evenly matched, Team Proton and Team Electron, always balancing each other out, while the neutron, refusing to take sides, has no charge at all. Example, let's consider a neutral carbon atom, which has 6 protons. If it's neutral, how many electrons does it have? Measurements of mass. When it comes to mass, protons and neutrons are almost identical in weight, heavyweights in the atomic world. Electrons, on the other hand, are the lightweights, contributing almost nothing to the atom's overall mass. Example, in a helium atom with 2 protons and 2 neutrons, what's the mass number? It's 4. 2 protons plus 2 neutrons equals a mass number of 4.
Atomic forces. Now let's talk about the forces holding this atomic party together. Electrostatic force keeps electrons in orbit around the nucleus, like the way gravity keeps us grounded on Earth. But within the nucleus, protons should repel each other since they have the same charge. So why don't they? It's all thanks to the strong nuclear force, which is like the glue that keeps the protons and neutrons stuck together.
The scale of an atom. To give you an idea of how tiny atoms are, imagine the nucleus as the size of a marble in the center of a football field. The electrons would be zipping around in the stands. So yeah, atoms are pretty small, but they pack a punch. Atomic and mass numbers. The atomic number of an atom is simply the number of protons it has. It's what makes an atom, say hydrogen, with 1 proton, or chlorine, with 17 protons. The mass number is the sum of protons and neutrons. Example problem: chlorine, 35, has 17 protons and 18 neutrons. What's the mass number? Easy. 17 plus 18, 35. Isotopes. Atoms of the same element can have different numbers of neutrons. These variations are called isotopes. For instance, most chlorine atoms have 18 neutrons, but some have 20. These are chlorine 35 and chlorine 37, respectively. Isotopes and atomic mass. When we talk about atomic mass, it's an average of all the isotopes' masses, weighted by how common each isotope is. So, even though chlorine has isotopes with mass numbers of 35 and 37, its atomic mass isn't just 36. It's closer to 35.5, because chlorine 35 is more common. Ions.
Atoms can gain or lose electrons in chemical reactions, creating ions. Lose an electron and you get a positive ion, or a cation. Gain an electron and you get a negative ion, or an anion. You can use symbols in the letters themselves to kind of help you remember which ion type is which. The word anion has a negative sign in the capital letter A, And the word cation has a plus sign in the letter T.
Example: a sodium atom has 11 protons and 11 electrons. If it loses one electron, what's its charge? It becomes a sodium ion, symbolized as Na+, sodium symbol with a plus sign written in superscript. It has a +1 charge because it now has one more proton than electrons. Why is this important? Understanding atomic structure is crucial for grasping basic and advanced chemical principles. Mastery of subatomic particles, atomic forces, and isotopic variations provides a solid foundation for further studies in chemistry and physics.